We've spent the past 6 lab sessions just designing combinational logic circuits. In 1620 last year, you were introduced to the fundamentals of sequential logic circuits, designs such as flip-flops, registers and counters. In this lab, we're going to look at how we can build these designs in Verilog and what that implementation actually looks like on an FPGA device. Now, we'll just be looking at simple sequential circuits to get an idea of how to make them and how they're implemented. For more complex systems using state machines and full sequential RTL, you'll have to wait till the level 5 FPGA module. To begin, it's worth us recapping what you already know about sequential circuits from last year. Sequential logic circuits are circuits where the current output depends on the values of both the current and previous inputs to the system. They have the ability to store historical information, and for this they require some memory. Memory in sequential circuits is made up of any number of registers, each of which is comprised of several flip-flops, the fundamental memory component of a sequential circuit. The information that is currently stored in a circuit is known as its state, and as time progresses and inputs are changed, the state of the circuit changes as well. The majority of sequential logic circuits are synchronous. This means that a clock signal is applied to the circuit, which facilitates a change in state of all circuit elements. The circuit state will only update in a change in logic level of the clock, which can either be a positive or negative edge. In order to understand how sequential logic is implemented on our FPGA device, we need to take another look at the logic elements on the chip. Each logic element contains a single D-type flip-flop. It acts as the fundamental logic element for all of our sequential designs, in the same way that lookup tables do for combinational logic. All of our synchronous logic will be built out of a combination of these flip-flops and the lookup tables. If we need other types of flip-flops, such as JK or SR, we'd need to build them ourselves, and they would be implemented using this specific architecture here. The input to the D port on the flip-flop can feed or fan in from a number of places, but for the small designs that we're doing, this will almost certainly be the adjoining lookup table. Data out of the flip-flop can also be fed back into the lookup table, allowing for logic operations to be performed depending on the current output state. By writing some logic for the lookup table using this feedback loop, the logic element can be made to act as different types of flip-flop. This allows each logic element to form the basis of both complex combinational and sequential logic designs. To further extend this functionality, the flip-flops can make use of dedicated clear, load, enable, and reset signals to become even more sophisticated. Each logic element can be used as a single-bit register. When we use multi-bit registers in our designs, the Quarters compiler will try to assign logic elements in a single logic array block to be part of the same register. This allows for incredibly fast designs and maintains consistency with regards to propagation delay times. It also allows for dedicated functions like load and clear buses to store or empty large registers in a single cycle. We can use a mixture of registers and combinational logic to create complex sequential circuits. Quarters will then optimize these designs into a sequence of registered logic elements, utilizing both the lookup table and register elements of the macro cell, often at the same time. As we know from last year, synchronous logic requires a clock to run. Synchronous sequential circuits change state on a clock edge, and therefore the modules that we write will need a clock input to drive them. FPGA devices have dedicated clock pins which can be used to drive the circuit. These pins are fixed, we can't just use any old pin unless we've got an external clock source, and they're clearly labelled with a clock icon in the pin planner. These clock signals are of a fixed frequency, usually in the order of megahertz. On the MAX10 device that we're using, we have 3 clock signals available, one at 10 MHz and 2 at 50 MHz. You can find the pins which these are connected to in the user manual. These clocks are generated by an external clock generator chip on the board, which is driven by a 24 MHz crystal. Now, when creating a digital design, there's rarely a one-size-fits-all solution to the required clock speed. In complex systems, different parts of the circuit will require different clock rates, sometimes orders of magnitude apart. Imagine a system which reads from an ADC and outputs a visualization of the signal's frequency domain on a VGA monitor. The ADC could be at any frequency, it depends on what we're sampling, but let's say it's audio, and therefore it will need a sample rate in the kilohertz range. Our module to communicate with the ADC chip retrieves samples through a serial link and would therefore be clocked in the kilohertz range as well. These samples will then be clocked into a FIFO buffer to build the frames for our frequency transform. This process isn't particularly time sensitive, so we'd probably clock it at either the system clock speed in the megahertz or use the same clock driving the ADC in the kilohertz. Now we get to our frequency transform. It's likely that we wouldn't be coding this ourselves from scratch, as it's a very complex design, so we can assume that we'd be using third-party IP here. Due to the high number of clock cycles required for one transform, we'd want to run this as fast as possible, so somewhere in the megahertz range. We'd take the output of our FFT and use it to build a frame to display on the monitor. Now, if we were really smart, a lot of this could be done with combinational logic, but we'd most likely need some sequential logic to process the output information into something more useful than a raw FFT output. So let's say we do this in the megahertz as well. Finally, we pass our frame to our VGA driver to display it on the screen. VGA is an interesting protocol when it comes to clocks, as it requires many in different orders of magnitude. The main pixel clock is at megahertz, the horizontal and vertical synchronization clocks are kilohertz, and finally the frame clock is either 50 or 60 hertz depending on the monitor type. In order to provide these custom clock rates, we would need some circuitry to generate periodic signals of a different frequency to that of the hardware clock. A phase lock loop, or PLL, is used to generate a signal which multiplies the hardware clock, generating a higher frequency. On the other hand, a clock divider is used to generate a signal which divides the hardware clock, which generates a lower frequency. Now, PLLs are too complex a circuit to cover at this stage, so in this lab we'll take a look at clock divider circuits and how they can be implemented in our FPGA designs. A clock divider, or frequency divider circuit, is a circuit which takes an input signal of frequency Fin and generates an output signal of frequency Fout is equal to Fin over n, where n is an integer. If n is a power of 2, then our clock divider circuit is relatively simple. We can create a binary counter circuit and use the output stage for each increasing power of 2 division. So the first stage divides the clock by 2, the second by 4, and so on and so forth. By feeding the inverted output from each flip-flop back into itself, we toggle the flip-flop's state on every other clock pulse. This inverted output also acts as the clock for the next flip-flop in the chain, meaning that each flip-flop generates a signal half the frequency of the previous. If we want to divide by an integer multiple that's not a power of 2, we'd have to get more creative. We could build a circuit which counts each edge of the input clock and passes the value to a comparator. When the comparison is true, we can toggle the state of a JK flip-flop. The output of this flip-flop would therefore be an integer division of the input clock, dependent on what value was in the comparator. So in this lab session, you'll be building your first sequential logic circuits to put on FPGA. We'll create a binary clock divider to divide down the hardware clock to a reasonable speed and use it to drive a counter. We can then bring in the modules from last week to display the count value on the 7-segment displays.